like to introduce Samuel. He's going to talk about distance correlation for market graphs. We had a few talks on market graphs today, and distance correlation is a different way to assign edge weights. So take it away, you have 20 minutes.
Okay. Thank you, Peter. My name is Samuel. I'm currently working as a data scientist in Oak Valley Health, but this talk will be based on my master's thesis, the work I did, which, as Peter rightly described, is a distance correlation market graph. So I'll be going through the introduction, talking about the background and motivation for this work, and I'll also be talking on the methodology. I'll be showing you the results and the conclusions, which I'll highlight our main contribution in future works. So this might sound like a repetition because Paz already covered most of the aspects that we're talking about. But just as a reminder, where we have the stock market graph, where we're representing the relationships between the stocks in a financial market. This is particularly important because this is the crux of what we do here with the distance correlation market graph, where it's this relationship, this particular way we evaluate this relationship in a market graph is what we actually did this paper on. So predominantly it's based on a Pearson correlation, or other papers have tried mutual information, Kendall correlation, and all other types of way to associate this particular relationship. But for this paper, we evaluate a metric called a measure called distance correlation. So now I want to show you the motivation or background behind us going into this evaluation of this relationship, why it's necessary for us to evaluate whether Pearson is sufficient enough to determine this, the way we create this market graph for stocks. So we take a look at this scatter plot of the returns for these two stocks, Dollar Tree and Autodesk. We can see visually, there's a sort of relationship. But when we go into Pearson correlation to see the Pearson correlation coefficient, the Spearman and the distance, it tells us that the coefficient is 0 for Pearson. It tells us for Spearman is 0 point something, telling us that there's no linear relationship, or there's, to the layman, there's really no relationship between these two stocks. But when we use distance correlation, we see that there's sort of a relationship, and that is what we're seeing visually. And when we go over to this table we have over here, we see that Pearson is not able to actually show a relationship for nonlinear relationships, and that's what distance is able to do. So we see that for all these defined relationships between y and x, distance correlation is able to give us a coefficient that indicates there's a relationship, and that would be particularly helpful. So if we cover the basis, we hope that this will give us a more robust market graph than what we have already. So now I would like to discuss what distance correlation is. It's a non-parametric measure of dependence that captures nonlinear relationships between variables and is not sensitive to the scale of data. This particular coefficient was introduced in 2007 by Gabor-Szewski. Sorry if I'm butchering the name. So it was introduced in 2007 in this paper. And I would just want to highlight some of its benefit. So like we know for Pearson, Pearson correlation coefficient of 0 does not indicate that there is no relationship between the two variables. But for distance, we can be sure that when the distance correlation coefficient is 0, there's really no relationship between these two variables. And there's no dimensional limit. And for distance correlation, it's versatile, meaning that it does not, it doesn't have much assumptions. There are no really much assumptions compared to Pearson or Spearman. So this can handle a lot of different types of data where we don't have to be worried about the assumptions making when we're doing this correlation coefficient. So now let's consider a graph with the vertices and edges. Many people have come here and they've talked about how to build the graphs. This is nothing different. We're still building it the same way, where the vertex represent the stocks and the edges are the connections, which here the difference is that we're using distance correlation. And to determine the edges, we want the connection to be the dissimilarity between these two stocks. So between the two vertices, we want the edge to be the dissimilarity. And what distance correlation gives you is the similarity. That's why we do this transformation here. Traditionally, for the market graphs that have been constructed using Pearson, what is done is the transformation below. But for distance, since this interval is between 0 and 1, where 0 is no relationship and 1 means there's relationship, so we just do 1 minus the distance correlation, and we're able to get the edge weights, which we use in constructing our weighted graph.
Sorry, what is R?
Oh, that's the distance correlation coefficient. So this is the distance measure that we're using for the edge weight.
1 minus R. What is R?
R is the distance correlation coefficient.
Oh, okay.
Yeah.
Yeah.
Yeah. I'm just trying to explain the edges, how we build the edge weights.
Sorry, I had a brain.
No problem. So after we build the edge for this fully connected weighted graph, we want to analyze it, and the first thing we do is the minimum spanning tree. The minimum spanning tree, as you know, is a representation of where we're trying to prune the graph to have a graph where all the nodes are connected, but the nodes are connected and there are no cycles, and it's connected to the minimum weights. So this is an example. We use Prim algorithm. So given this network that's fully connected, we pick a vertex, and we choose the shortest weight in the shortest edge from this vertex. We choose the nearest vertex that is not in the solution, and we do that till we get this fully connected with no cycles, and using the minimum edge weight that we can find from each iteration. And we do that because our graph is a fully connected stock graph with many nodes. So we don't have time for this optimization at this point. So we just have to pick, and we use this algorithm. So this Prim's algorithm is better for denser graphs, which is like ours, the stock market graph. And sorry if I forgot to mention, our case study is the S&P 500. So we have about 500 stocks, so 500 nodes. So now this is an example of the final result after we construct this graph. This is an example of this, and the color combinations are indicative of the gigs classification, where the gigs industries, and the 11 of them are color coded into this graph. What we see here is what intuitively we know, that these stocks together they move together, though in the same industry. They're close together with the exception of some, which we know, where they talked about, like Amazon is classified as was in a certain industry, but we can see its market share in other industries, like in the retail and every other thing. So this is what we're seeing in this graph. But what is important, what is interesting to know is that when we look at the topological properties, we want to compare the topological properties of the two graphs. That is the one built by Pearson and the one built by distance correlation. And we evaluated the longest distance, which is also known as diameter of the graph. So that's the longest distance between one node, the largest distance we have in the whole minimum spanning tree of our graph between one node and another. And we also evaluate the average distance. That's the average distance if you take for you to get to one node and the other. What we notice is that we evaluated 2 time periods. And these 2 time periods are significant in the term that January 2020 to June 2020 was the period of COVID, where there was a bit of a market downturn. And January 2015 to 2022 is seen as a bit of a stable time, or where we had the economic boom. And what we see is that for the properties, longest distance and average distance, for the stable period and the long time, we see about similar properties. But when we go into the period of perceived market crash, there's a contraction, or there's a shrinking of the longest distance and average distance for the distance correlation. And this is in line with the paper published by Onela, saying that in times of market crash, we expect our graph network, our market graph to shrink. And this shrinkage is seen vividly in the distance correlation. This shows that it's a better measure of the properties between these nodes, between the stocks. And that's what we're seeing here. And this is the representation here, whereby we're seeing during the market crash, the way the graph shrinks, and during the market crash, there's really no much different for the Pearson correlation. However, what we're seeing is that during the market crash, the sectors are not really defined as they were for the stable period. And here we look at the degree centrality, where we're studying, this is based on the nodes. We're looking at how many degrees each node has, and we did it based on the industries. So we did the aggregation based on the industries, and we're trying to see which particular sector was the most influential over this period and comparing it for the two methods. And we see a recurring theme, which we know that the financial sector has the most influence in this market graph. And we also see from 2015 till right now, the increase in the influence from the IT sector, which represents what's happening in the stock market. So this gives validation to the work we're doing as it captures what is exactly happening in the stock market with our graph. Going forward, we try to give ourselves validation in the area of index tracking, which Paz discussed. So in his methodology, the method of connection was Pearson correlation. And with this change, we do exactly the same thing we do, but the difference is that for our edge weights, we use distance correlation. And we wanted to compare the tracking error. And now we see that for the FTSE, Nikkei, Russell, S&P, we get better tracking. We have a lesser tracking error than he had for when we use the distance correlation, especially in times of market crashes. And this helps us to know that distance correlation is a better method to use in terms of constructing your market graph. So the question we were addressing is that, are we enhancing market graphs using distance correlation or Pearson correlation? And we believe we were able to answer with evidence. And we see that the key finding is that distance correlation captures the non-market relationships, especially during turbulence, better than Pearson correlation. Thank you.
Thank you very much, Samuel. Any questions?